you very much indeed. Yeah. I'm continuing where we left off last time, and now we have a nice and review of what we did. So there was motivation about our test and ways of doing more things very involved, and how that's promise the bottom was actually realized, and then there's Modal HoTT, which takes some work and worries about exploring it. But I think there are two short ones. So this is the amount of story, not just really a few decades ago. What I'm trying to show is some sort of new story. So, I argued last time is a review that the principles of physics actually well reflected in hypothesis theory versus principle actually. Theory, which is not in art. So the second principle is called the principle, which I argued with. Okay, geometry. If you just implement it by hand, again, by just throwing in test spaces, spaces that were infinitesimal graded extensions of Cartesian space that just implemented this principle by hand. So this was a pedestrian approach to just building a model that realizes these things. Right? So with these formal spaces, they were extended by infinitesimals, and then we just said, okay, let the infinitesimals be allowed to be super commutative. And that alone gives rise to a mildly interesting sequence of junctions between the sites. Kind of the interesting point is that due to the infinitesimality here and due to the super algebraic point here, these modalities kind of increase in such a way that it becomes more pronounced as we pass to the sheaf toposes over these, which are indicated down here. So my overall infinite topos over H, and the others I denote by the localized test. So this is the bosonic part. Here we have no super yet. This is the reduced part. We have no infinitesimals. So there's a sequence of toposes now equipped with the left-Kahn extensions of all these maps here, which checks it does descend to the sheaves. And now, since we now toposes, all these adjoints have a further to right adjoint by pullback and by Kahn extension, and they fit into a larger system of adjunctions like so, which kind of filter the big topos, stratify it very vividly so by these sub-aspects that every type now carries. There's a super aspect, a formal aspect, a smooth aspect, and we can map back and forth between these. That was extracted by turning all these adjunctions that go back and forth between these subtoposes into lots of modalities that just act on the big H here, just keep projecting down and re-including, or projecting just halfway down and just So I'm being quick here. So just playing this looks a bit like music, doesn't it? Playing this game gives the system of modalities, which one then just finds as a phenomenological observation, are what exactly one wants to use when one does super geometry or does any constructions. So here's the right first there was the bosonic projection of the bosonic body. That's a standard operation that geometers do all the time. Rheonomy I mentioned has a big role in supergravity. This immodality got fame as the construction of the Ram stack by Thomas Simpson. There's a big role in the theory of crystals. Turns out these two here are exactly what one needs in order to formalize differential cohomology. Yeah, Felix wrote his thesis about this one here. And so the point here is that even though we started with the site and just building everything by hand, we end up with something that does look like it's a good abstract context for proving things. And I mean, this is ongoing work, but many things, right? So many theorems that I don't know could have proved using the exact data of the site actually follows abstractly from just the fact that we are in an infinite topos equipped with the system. So the idea is that the more and more we find theorems that are just entirely determined by just such a system of modalities, the more we get confidence in the claim that actually that is what should define super differential geometry. That's not established, but I think there's some good indication. So, and then there was a curiosity here that in that model, actually the guys in the middle here happen to be A1 localizations as a typical homotopy theory. In particular, the top guy is the localization at the superpoint, which is kind of the odd incarnation of the real line now, the super incarnation of the real line, which has this kind of curious effect that somehow we discovered the superpoint. If you now believe that the axioms, that the system of modality is actually sufficient to determine supergeometry, then the thing that is the superpoint in the model here actually will behave like the superpoint in any other model. So that is maybe our abstract. And then I switched, I glossed over something, which maybe I'll recall later today, but I'll just gloss over it again. There was this claim that if you just regard the superponian form now in homotopy theory, regarded in homotopy theory as an object in form kind of iterated universal centric, it's kind of a Whitehead tower. There's stuff that appears which is well known in string theory. For instance, that will concern us a bit. There's something that appears here that is kind of that is the Super-Minkowski space-time of 11 dimensions with 32 fermions in it. This is a mathematical classification process that discovers this from the superpoint. And if one analyzes further, that's where I want to start off today. If one analyzes further, one finds that to go with this tower of extensions, there is a co-cycle on that 11-dimensional Super-Minkowski system. So there's a map, the rationalized force sphere, the realified force sphere, in the super topos, which is a co-cycle in homotopy, in the non-abelian cohomotopy theory represented by the force sphere, rationalized though, but on the super space time. That encodes the what physicists know as the curvature of the WCW term of the Green-Schwarz M2 and M5. So this is something kind of important, but as we don't know that yet, maybe it just tells us that just looking at super homotopy theory, and starting with the sort of simplest homotopy object we have in there, we discover that somehow the formalism the theory is telling us that we should be interested in cohomotopy. We should be interested in mapping to the force sphere out of spaces that are maybe locally modeled on this. So this was an infinitesimal construction here in rational homotopy theory. So what I would like to do now is I want to ask, does the formalism know how to handle that there are spaces that locally infinitesimally look like this, whose tangent spaces are like this, and on which maybe this co-cycle globalizes. And this is where the constructions of quantum geometry come in, that are considered in this synthetic cohesive context, and then told Felix to maybe try to formulate in a homotopy type theory. So let's skip over the equivariance for a moment, and just think of this Cartan geometry business that Felix formalized in his thesis. So it's an aged idea going back to the 1920s by Élie Cartan, much superior to in generality and power of expression to maybe the standard Riemannian geometry, which is but a special case of it. Cartan geometry also subsumes conformal geometry, all kinds of variants of geometries. And it's based on the simple system that physicists know as the Cartan moving frame method. It's evident enough that physicists can understand that. So you say, let's suppose we have a curved space. I'm just drawing a torus, just for drawing. Well, Isham draw that torus actually. So it's easier to draw. So we want to say somehow we want to equip that torus with geometry by saying we pick a fixed reference space which is linear, or in fact, in the type theory formalization, it just is required to be a group. There's just supposed to be some translation action. So we require very little. In fact, Felix in the end reduced it to even less than I had. It doesn't even have to be a group, just has to be what a left H space, something, right? Is that right?
I called it homogeneous. It's not really matching up with something from the literature. But the group, infinity group structure would be okay, or just being able to move around. So in the examples to every other point.
Right. Thanks. Yeah. Yeah. So there was a for me a good payoff and proof of concept of this whole approach of trying to formalize these things. So initially I gave Felix a list of diagrams that I had written, with which I had proven some things. I said, why don't you just formalize this? And Felix went through this process, I think, first he formalized my diagrams, and then at some point he said, what the heck am I doing here? And then you noticed that all this can be done much more elegantly without changing the context, just thinking about it synthetically, and he ended up finding alternative proofs and stronger proofs. Some of the things I had originally done thinking as a category theorist using just the internal language of the top. So I thought that was a very good example of how it can be helpful, even if you're not interested in type theory as such, to formalize stuff because you learn about your subject. Anyway, so the applications we're thinking about should think of this as being, so I'm writing Super-Minkowski here, but just first think of it as an Rn. Suppose we want to model a real n-dimensional manifold. The tangent spaces are Rn's, and we're just remembering here in this kind of geometry picture, we're just remembering that this is group structure on Rn just by translation or to the group structure. And we're using this to say what it means for things to be code and free, for instance. So roughly we characterize Korsch spaces by saying, well, there should be the tangent spaces should all look infinitesimally, should all look like an infinitesimal neighborhood in this model space, and should move around in a controlled way. Okay, so this slide is extremely dense. Maybe we should write some things to the board. Let's see how we have some other things to say too. So, so where's the chalk? So in using our modalities, using that immodality, we can now formalize a few things. So, for instance, we have our so V will be the notation for this local model space to make you think of vector space, but it not be the super space time. And we have a unit map eta im, or maybe eta im V, to its im version, where im is the thing that I haven't maybe said that it contracts away the infinitesimal neighbors. So if there's 2 points that are infinitesimally close to here, they get identified here. Or alternatively, you can think of it as being an operation that inserts an infinitesimal path between 2 infinitesimally neighbor points. So it's an infinitesimal version of the path infinity group point. And so what this fiber product here says, it says we should take the fiber product V, that's what I've drawn on the left, over im V via its unit with a point. So V being a group or left H space or something, one axiom that it has a neutral element. Yeah, let's call it E maybe. That's the point. And since im is a left and right adjoint, well, since it's a right adjoint, it sits right in the middle of the big diagram. It's the centermost piece of everything. It preserves the point, the terminal object. So you can think of this as being, so this is im of the unit inclusion. So that's canonical morphism. And we're told that so this notation, remember these blackboard boldface D's were supposed to be the infinitesimal disks on the point. So I'm saying, there are many of them. I'm saying it's not the one around E and D, so it is some decoration. I'm always unsure. It will be different from what Felix shows, and different from what I've chosen elsewhere, maybe. So we're supposed to choose this this pullback now, and I'm claiming this gives the infinitesimal neighborhood of the neutral element in V. In that picture, that is supposed to, here's this magic magnifying glass. It's supposed to be right the infinitesimal neighborhood around chosen origin. And how can we understand this? So what's a map into this by the pullback property? Suppose we have anything else, maybe an S. We want to understand what is a map to this thing here. Well, it's a map to V, subject to the constraint that the unique map to E makes this diagram converge. But this means that as we compose here, we must have the constant map on the point. With this map, like we said, what it does, it just identifies all infinitesimal points. So a guy becomes constant here if it was just all taking values in the infinitesimal neighbors of the neutral element here. So that's my category theorist way of saying it. And internally, but I won't try that now synthetically, you can just say it more elegantly. And so in this fashion, we keep going. The next step is the key proposition, which I saw at some point as a formalization, which then Felix formalized. Oh, sorry. Have I actually defined V manifold? Oh, I skipped over that. Okay, let me do that now. The eraser. Sorry.
Oh, it's hidden.
Thank you. Well, good. Yeah. So we have the infinitesimal disk. So first of all, we want to say what it means for something to be locally modeled on this infinitesimal disk, and we do a generalization of this diagram, which we just had. We say a morphism, a map, in our infinity topos, say F from X to Y is so the algebraic geometer would say formally Dal, meaning it's infinitesimally like in a Dal space. The differential geometer would say it's a local diffeomorphism. Really, it's the same equation. If one way of saying it is to say that it's immodal as an object in the slice. if it is im modal in the slice topos h over y. So the X modality goes to the slice. Let's call it subscript y. And so we're asking that f is f. What this means, if we unwind it, just talk about it by walking here, the modalities in the slice is X, they're given by the pullback factorization. So they're given just by the kind of diagram I just drew before. So it says that you cannot fit it here or maybe fit it here. So this means that we want to check if f from x to y is a formally a tau map, if it's iso onto the formal disks around each point up here. And so we look at the unit map here, im y to im y as we did before, and then we put im x here, and here's im f. That's a general theorem that putting this back is applying im in the slice to f. So that means this guy is im modal precisely if this is a pullback, in which case then also this is actually the unit of x. So we say a map is a local diffeo if the naturality square of the im unit is a pullback. And one checks, yeah, maybe I won't do this now. We have many things to say, maybe more interesting. One checks that this comes down to the traditional definition of local diffeomorphism in the model between manifolds. Right, so we haven't even defined manifolds yet. So what we want to do now is we want to say, Felix, do you see it on the camera if I draw here? Is
yeah,
okay?
yeah.
So we want to now say this first axiom, we'll truncate it. Let's look at this here. We want to say that we have a V fold, that we have a space that is not equal to V, but is locally modeled on V. And locally in the strict infinitesimal sense, or in whatever sense, so here's an X. In our super homotopy theory. And we want to say infinitesimally looks like V. Now these immodal maps have just the property that they send. Maybe I should draw a picture. If you take X here and Y here, and if Y looks like so, with this point being f of X, well, this would be maybe too small already. Then X may be something like here. This is an X. So it means that for every point here, if you take the halo, the infinitesimal disk here, and map it down to here, that this is an ISO, that this identifies these disks. But then there may be another disk here, so it's not globally an ISO, but locally, right? That's what's called local diffeomorphism. So this halo here gets identified there. So it maps formal disks to formal disks. And so what we can do is we can say, well, suppose there's an immediate space U, which is supposed to be reminding you of the unit of the standard notation for open covers. So we want to say that U is like an open cover of, say, an N manifold. Then the usual open cover will consist of lots of copies of Rn, which hints of V's. So it will be a disjoint union of V's. So we can send them all to here in a way that is a local diffeomorphism. It's a bunch of copies of V's. We send it to this one V. And so this will be, so I write this as with an at symbol here. If this is a pullback, I write it for formally a tau. And right, so this map alone just says that somehow U is locally like this. And then, well, but X is also supposed to be like this. So let's just require this also to be formally tau. This just kind of carries the unit in a kind of correspondence, carries the disks over here. And then all that remains to do is to say that we've really hit everything. So this might be a priori much larger. We might be, say, Rn, but U might just consist of unit balls in Rn. That would still be a formally tau map, but we wouldn't be covering V. But now we want to say we cover V, but that's very easy. We just say, yeah, this is something one, of course, knows from Popper's theory, just saying that this is an epimorphism, effective epi, or just epi in type theories, is that saying this in the topos is already sufficient to say that this is a surjective open cover. So we have a surjective. We have an open cover, that's what this being surjective means. Epi, 0 truncated. Sorry, minus 1 truncated. Is morphism, and it's étale. So that's it. That turns out to be the different. This is a V-fold. X is V-fold. If there is U and V in these maps. That's the definition. And that looks very simple. That turns out to be it. Well, first of all, you show that every ordinary manifold, now the unita embedded into the topos, becomes a V-fold via its standard covers. But then the interesting thing is, from that definition alone, follows now quite a few properties of manifolds that take the differential geometry textbook, like 50 pages, to build up. And one of these is this fact here, which I have already previewed accidentally, that every V-fold from just this data, you find that there's a map from any such X, if it has this, if only it has this data, to the classifying space, the delooping of the automorphisms, the internal automorphisms of the formal disk in V. That turns out, if you unwind it for what it means in the standard examples, that is what is known as the frame bundle. So that's the principal bundle to which the tangent bundle is associated. Or rather, it's the jet version of the frame bundle here. Since we don't know what in things is infinitesimal, in might think first order infinitesimal is all there is, then it's on the nose. But we like to think of it as being the formal guidance, the jet frame bundle. Yeah, please.
Those are just automorphisms, not necessarily pointed automorphisms.
Well, these are necessarily pointed because these formal disks, by junction, they take the point to the point. That's because the point. That's because this co-reflection. The point on the formal disk has to go to the point of the other formal disk.
Externally, but internally, the text or the objects are pointed automorphisms.
That's right. That's true. That's true. So that's right. Yeah. Right. So okay, that's true. So it's just the automorphisms. Yes, that's true.
Yeah, I mean the point is that the internal odd dv will be a bit too big because we're not looking at pointed automorphisms, but we won't see the difference if we map into it from a reduced space.
Yeah, we'll see this go away in a second. Yeah, so right. So that is true. So for instance, if let's see that appear in a moment. This is now a superspace actually with automorphisms. So we'll put a Minkowski space-time here, and then the bosonic part of the underlying say bosonic part of this here turns out to be just a spin group. But then there's also super thickening of the automorphism group itself, and we'll remove that by asking for group homomorphisms, for reducing the structure group to the group automorphisms. And they will in particular preserve the point. Yeah, I'll get that just a second. Yeah, good point. Thanks. I guess you're asking something, right? Is that the case? Or are you?
Is in this formalism, can you go from the jet frame bundle to the usual frame bundle? Like, can you interpolate between these formal things and the
right, so this is something, yeah, we haven't, no, this is not implemented. Yeah, we've thought about this. One can try to have more in modalities that stratify or honors of infinitesimals, maybe interpolating from zero infinitesimals that have been going on to the germs. We thought about this every now and then, but never. Felix, have you ever realized that in any form?
Not
That's right, we can do that. It turns out that's is the jet version that we're going to need in the application that I'm headed for. So I'm actually quite happy.
The issue is, even if you stratify by these truncations, like you might have a formal thing, but you don't know if it comes from a real thing.
Well, if we have the stratification, then we can just use the corresponding im n for nth order, and we'll get the nth order jet bundle, and maybe it's the first order jet bundle would be the ordinary tangent. But it turns out to actually be useful to right, so that's the general feature of these synthetic axiomizations. They usually apply to more models than you may have thought. That's the effect we see. So you may have thought you're axiomatizing the tangent bundle, but then depending on how it is implemented, the way I implemented it, it gives you this jet frame.
Is there any distinction between formally étale and étale in this setting? Like finite disk conditions, like the other algebraic geometry?
So there's no condition on the fibers here that the fibers have to be finite. So This observation, I should say, that formula HoTT can be axiomatized this way. This is in some quite mysterious language in the preprint by Kontsevich and Rosenberg, which never appeared, published, but it's on the server of the Max Planck Institute. And they observe that formula HoTT without the finiteness condition of the fibers can be phrased this way. Well, you won't see the Spurbeck diagram in there, but it's in there. And that the local diffeomorphisms equivalently are phrased this way is one can find in some article by Anders Koch. It's not very prominently highlighted, but I found it at some point in there. So this is a known construction, even though it's not really easy to recognize as in the literature. So this is where it gets interesting here. Now we have, for each manifold, we have this fiber bundle associated with it. And that's where this cardinal geometry business comes in. So it turns out maybe 90% of the point of this cardinal geometry is that you want to say there's geometry encoded on your manifold X. A priori it's just a manifold. We're reducing the structure group. So this thing is called the structure group of X. For obvious reasons, there's some group which controls the structure here. And what we can ask now, do I have this on the board? Yeah, we can ask now, given any group object, and a homomorphism, a group homomorphism, from G2, so we fix our X, or we fix our V, and then we ask for a group homomorphism from G as just a plain map from VG to V ought DV. So you should think of this as this. Maybe I should amplify this. This ought DV is a stand-in for, it's bigger in general, but it's a stand-in for what in the ordinary model would be GLN. So explicitly, if you choose Rn in the standard model, if you take the external part of the automorphisms, if you take flat of that, the underlying group is, if you do the first order version, then it's GLN. Right, so now we can say, okay, this is our manifold, equipped with, did I give it a name? With this frame bundle. So then we can ask, we got both of these objects, say, in the slice, and we just ask for a cosine, which is just for a map to here, which of course, we don't always write this, means that you've also chosen a homotopy here. So that means that this is called a reduction of the structure group in standard literature. For evident reasons. That was the structure group before. Now we're saying actually all these transition functions that say all these frames transform kind of as we move between patches, parameterizing our manifold. All these transition functions that a priori could live in the big group or TV, not just in G. So that's something that becomes easy to say. And then there's a fact to be shown, which is simple but turns out to be interesting because it's glossed over in this form in the standard literature completely. The standard literature tries to or concentrates on RNs with the translational structure. It just observes that if X, so V itself is easily tautologically a V manifold, a V fold, just by taking the two maps to the identity. And so, so we can ask if there's a given G structure on V for any group G. And so standard literature takes this to be Rn, right? Everything is contractible, so they just say, well, of course, you can always find a map just sends everything to the point. Just do nothing. It's just a trivial map. Now, we can't do actually this generally at type theory. Also, there's a better answer. So V has structure. V in itself has this translational structure, say group structure or Vellanian H-space structure. And what we can do is we can kind of ask, suppose you pick one format disk here, then use left translation with respect to the translation structure to transport it around. And that should give you the structure. That turns out to have a nice formal answer. So there is, how did I call it? Did I call it anything? Oh yeah, here. So we should call this E, by the way. Aha, maybe I should have said this here. Sorry. So this E is also one of the standard, this homotopy is one of the standard literature also called the field line. Field line. This comes from the fact where these groups are or are thought of as matrix groups, usually GLN and ON or something. And then this field line is a map from some manifold to the general linear groups. So it's a bunch of vectors, if you wish, that transform sort of in one of the indices as GLN and in the other index as G or ON. So if you write this out as a tuple of vectors or covector fields, then it looks like you have on each point of your space chosen legs. And that's why it's called geometry from many legs field line. And so there's this canonical field line here on V itself, and I call it Li for it's the left invariant one. It's the one obtained by left translation. And that's super important for the supersymmetric thing we're getting at. The super Minkowski spacetimes have this curious difference to ordinary spacetimes that they're also groups, super translation groups. They're slightly non-abelian. There's precisely this bracket that you may have seen in supersymmetry that takes two fermions to a boson. That is the super bracket on super Minkowski space. I mean, it doesn't vanish, so it's not an abelian Lie super Lie group. That means that this left invariance on V is not completely trivial. There's a non-trivial group operation, and what one gets in applications is actually the left invariant framing here, which relates in supergravity what's called the torsion constraints of supergravity. So it turns out this simple fact, which kind of is almost the only thing you can actually say in type theory, reproduces a deep subtle fact in standard literature.
So this E here, it's constructed from the map over there, the map BG to BL.
So I'm saying, so you see, here I'm saying the reduction is a choice of such an E.
Oh.
For over any X, you can ask, can I find an E or not?
Yeah.
Or how many can I find?
Yeah.
And I'm saying on V particularly, there's a canonical guy here. There's a canonical choice.
But it must come from somewhere because G is arbitrary.
Constructed.
Yeah, it comes. That's what I tried to say. You use the group structure on V.
But G was arbitrary.
No, you can construct it for the trivial G.
Thanks.
And then you also have it for any G because the trivial one sits in
I see.
G.
Thanks for the question. That happens to factor through V1 if you wish. So there's a canonical left invariant G structure for every group on V, because there's actually one for the trivial group. It's just, sorry, now you look perplexed. That should be.
Now I look perplexed because I could do this for any X. I mean,
No, it just won't exist. If you, right? So I mean, the structure in this frame bundle knows about like how X is topologically non-trivial, how it twists around.
no, I understand. I'm not saying the choice is unique, but I'm saying this doesn't depend on V. I mean, if V1 is a point, then I can always project such a E for any.
Yes, so that's what I meant. So that's what the standard literature does. It just gives you that trivial factorization. But that's not the, yeah, right. It exists, but that's not the one we want. We want we can also construct the left invariant one, and that's the good one. Okay. I see, yeah, thanks for your question. Okay. So there's maybe one more question. Maybe not?
It's a question on that, the next thing. Whether this flatness coincides with the flatness of your flat modality.
No, yeah, well, it's related, but it's a priori a different notion, yeah. So, can I draw this somewhere? Maybe I didn't arrange my. So, was a major insight in an article by so where's my cable? Sorry. Yeah, how do you pronounce him? The French might help me. I don't know if it's actually French. Guillemin, or is that? Actually, that's now I can learn something in this conference. That should be the ideal conference to learn how to pronounce that name. So this guy, maybe he was American. Actually, I don't know. And in the early 60s, he realized what in modern terminology. So he doesn't say infinitesimals, that's clear what he's doing. He observes the following thing. So people had introduced before the notion of what it means for such a G structure to torsion-free or flat, and he observes, and they define it in terms of lots of B brackets and vector fields. And then he observes that this just means the following beautiful statement: the G structure is flat. So you can take this as a definition now, but the point is people had defined this in different ways, and then he showed it's the case if on each infinitesimal disk it coincides with the canonical one. With the one on V. So I'll try to draw it. This will be hard, or maybe I shouldn't try to draw it. Do you see what I'm saying? So we had a G structure here. Was this E everywhere? But now we also know that if we take a point, let me put it this way: if we take the formal disk in X around any point X in here, then that's by the fact that X is a V-fold. That's, can I fit it here? That is the same thing that is canonically identified with the formal disk in V of, say, the neutral element. That was the point of the cover being this formally taught. The tension spaces here look like those in V.
No. It's
So,
merely identified to, if you speak in type theory.
yeah, maybe I said that wrong. Yeah. Merely identified. Right. So we have a V structure here. Maybe I can fit it here. So we also have this canonical V structure. With the left invariant translation, and we have this included here. So we can ask that these two homotopies that now have this, they can be whiskered. We can ask them to be the same, actually, not to be homotopy. And that if that is the case, we would say that this G structure is flat. If this happens on form, if this happens if on each infinitesimal disk. So similarly, we would say is torsion free. Torsion is kind of the first order version of this. That's how it's called. Torsion free if this is the case on each first order infinitesimal disk, which we haven't exercised here. Or which one could it? So I mean, the statement comes from a classical constructor. We just write down these things. So that's another beautiful thing that comes out as well. So what we'll do now, we'll revise this.
Move the mouse.
Yeah, I think it went to sleep.
Oh,
Should I share my coffee maybe? So these are important concepts in Cartesian geometry that that we can now easily or have easily axiomatized in synthetic homotopy type theory here. And then maybe just to amplify so this is why Cartan was originally interested in this, to take this example where V is Rn, where so this is the first order GLN, we take ON, then this Vielbein is precisely the choice of Riemannian metric on your manifold. And asking it to be torsion free is exactly asking there to be, to be a connection, a Levy-Civita connection, which is torsion free with respect to that Vielbein. And it being flat means that this Levy-Civita connection is flat. So that's where this terminology comes from. So we're in a context here where formulating field ingredients of gravity is right here at our fingertips. And we've just been doing axiomatizing immodality. So that's why I thought this was an interesting thing to axiomatizing thesis.
So just to check, in general, being torsion-free and flat is a structure on a G structure. But in the case that DV is a set, it would be a property.
In the case that DV is a set,
Yeah.
Right. So there's that's okay.
Because I might put multiple homotopies between E and E left.
Yeah, that's right. That's right. Yeah. That's true. So you need to say how these are identified.
What I ended up with in my article is, I think, to say that the disks are merely equivalent, because I also only have merely the identification in the upper left corner in the big diagram here. So in the end, I just say merely. So I think it's always a property, at least the way I stated it.
Right. Okay. Yeah. Good. Thanks. Okay. So. So here's why this is interesting, and if you just believe this. So this is now going out of the stuff that we formalized, but this is just a fact that is true in that model. So there's some magic going on with this. Remember, I flashed at you this brain bouquet of extensions where I claimed that there's this canonical V appearing, which goes by the name R10 so it's like 11 copies of R, but then it has 32 odd coordinates and transform the reducible real spin 10, 1 representation. There's some object here which is a group, and it should be a group object in our age. As such, is called the Z equals 11, N equals 1 translational supersymmetry group. So it's not the full supersymmetry group, which would be a group of super isometries of it. It's the translational part of it, just like Rn is the translational part of the Poincaré group. Translational supersymmetry. Is there, sorry for that, I checked before, is there more chalk here?
It's in the box.
But that box is, and so what we can do is one way of finding canonical G's is that we say, okay, we had a super manifold which is modeled on this guy, so maybe I can call this now D 10,1 32. So suppose he has a super space which is actually a V-fold for this group. So you want to ask what's a canonical group that we can reduce to? Well, we can take the automorphisms that are group homomorphisms. So we didn't require this here. And then ask for these structures. And now it turns out that this group, in this case, this group is the spin.
What's the group structure on D10,132?
So it's the group structure. I'll give you the Lie algebra structure, right? It's a super Lie algebra structure. So super Lie bracket. Two is this thing. So we traditionally one writes P for the vectors in there. For momentum, these are the translational, visual translation operators, and they commute. Then traditional notation, we have these odd graded guys here. Their traditional notation is a Q. This alpha index. So these mixed terms also commute. There's one, so this is also a commutator, since this is even, this is odd. And now there's one anti-commutator, so a supercommutator of the Q's with themselves. That is a linear combination of the P's. That's the famous expression of supersymmetry that two fermionic translations get one ordinary translation. So there's some kind of fancy looking formula where you use the gamma matrix for we have a spin representation. There's some gamma matrices that go with this. They carry these two indices here. And there's really some charge conjugation matrix that goes with it too. So there's some matrix here, which is just the structure constant of the super Lie algebra that tells you that two fermionic guys pair to the translation. And right, so we have this setup, and it's kind of interesting because now, so this is like a super version of an ordinary bosonic manifold, and we just said that reducing to ON structure is choosing a Riemannian metric. But Sp9 is just a cover of ON, right? We first go to SON, which means oriented, and then unoriented. In fact, actually, if I don't put further constraints, we get pin. Unoriented state. There's no constraint. This has to preserve the orientation. So such a G structure is now in particular a metric. You can form the underlying bosonic pieces and get flat metric, but it's a bit more. So this E is now what they call the superfield line. So in addition to the reduction of the bosonic part, there happens a reduction of the fermionic pieces in here, which is the if you think of the ordinary field line as encoding the graviton field, then the super part is the gravitino field. So that's just a thing that happens in this model now. And well, we have the previous statements here. We can ask that this be super torsion free, which is where now this left translation invariance is crucial. This only works with that left invariance translation. And there's a curious fact in the literature from the late 90s. And this is all very classical stuff. It's not even real math literature, but it's a solid proof. That proves that the equations of motion of 11-dimensional supergravity, right? You say, okay, such a reduction of the structure group, that's a metric with its super part. It's like a field content of gravity. And now you might want to put a further constraint on this. So this torsion freeness constraint is equivalent to the equations of motion of the supergravity theory for what they call the vanishing bosonic flux. So it's a sector of the, but in particular, it means that the underlying bosonic piece satisfies the ordinary Einstein's equations of motion. So that's a miracle that I think doesn't have found all the attention into it. And so what we'll be interested in, since I'm just writing this down for our immodality, which contracts away infinitesimals, I actually asked this, what follows now, I'll actually ask this to be just what it is, which makes it actually a flat connection. And then you might say, well, then nothing much is left. Now you're telling us you're doing gravity, but everything is flat. That's kind of defeating the point. But now here's where the homotopy theory comes in, and it's actually far from defeating the point. It gets all the more interesting, is that X is not necessarily just zero truncated without slicing. It doesn't have to be a plain super manifold. It's in general a super orbifold. It can itself have automorphisms. And so we're really talking about flat super orbifolds now, and they have a very rich. Here's some physics remark for why this actually makes sense. You can see that this actually appears in far horizon limits of these brains, but I don't talk about this. So what's my time? So here's something I wanted to present now. So far, let's see where. So what I try to show so far, and we have to look at the time, is I give you this model that exists. We have some good experimentation of the modalities in here. Because it's Felix, Felix proved some theorems here, which partially proved, which give us good content geometry that works particularly with 10 minutes, particularly well in the flat case. The flat case, that's what I wanted to say. So we could work harder now and add more modalities maybe to resolve that, or we could just go with the flow here, follow the Tau of math. And that's, well, okay, it's telling us it should be flat. Let's go for it. And we remember, okay, we actually have orbifolds. And so what we really arrive at is now a theory of flat super orbifolds locally modeled on R10,132. And at that point, we should go back and remember this picture where we came from. What we really started out, we wanted to say, we had some infinitesimal information that we wanted to globalize over spaces. We did it for this space R10,132 itself. I indicated how this data alone, via the ghost of Cartan, induces curved supergravity spaces that are very different globally from R10,132, but look like it locally. But remember, there was more structure. I'm going all the way back now to this rainbow K. the whole point was that there emerged not just that superspace in itself, but it came equipped with the canonical cocycle, so the canonical map to the rational force field. So this is telling us that somehow there has something had emerged out of the super point that tells us we shouldn't just be looking at just the space itself. We should be looking at spaces locally modeled on this that are equipped with maps to something locally modeled on the force field, cocycles. Well, that is rational homotopy. There are many. So at this point, I don't have a full this step. So I want to make this the actual force field. I don't have a fully kind of systematic, God-given argument for why I should do that, but it's a natural thing I can do, and I'll just do it. So I'm asking now, what happens if we take our superorbitals locally modeled on this and ask for them to have cocycles in homotopy, degree 4. And that gives us the following picture here. So if you have any cohomology theory on a curved manifold now, you should ask for its twist inversion. So you should say, well, the coefficients is a given space, say S4, but it doesn't have to be constantly in that space. That coefficient may move around. And what may the force field move around by? So let's look at this corner here. So here the S4, that is the smooth S4, the cohesive, zero truncated force field, as opposed, I'm trying to distinguish it from its homotopy type, which is its shape. Right? And there's a canonical fibration, of course, of S4. There's a universal S4 fibration of the structure group spin 5 or O5, doesn't matter much, where this is for all these universal guys. Just comes from the fact that O5 acts canonically on R5, which is the ambient space in which S4 is the unit sphere. So these are the automorphisms of S4 by isometries. Then we form that would be ON, and then we form this guy. I should really do all this for pin, but somehow my finger was right spin. Okay, so this tells us that the force sphere, if we want to be looking at twisted degree 4 cohomotopy, its twist would be a map to spin 5. So it should be the tangent bundle that's twisted. So it says, okay, we should somehow have a factor of B spin 5 in the structure group of our frame bundle here in order to be able to have these twists. But now there's this curious thing called the quaternary which Ulrich and collaborators have actually gotten hold of in HoTT to some degree, to a homotopical degree. And it says that, as you know, let me just say it, that the 7th sphere, the classical 7th sphere, has 3 fiber bundles. Actually, a principal bundle, or S4. So this goes by the name HoTT, or quaternionic. So this for HoTT, this is for the quaternions. There's one for each of the 4 division algebras of these guys. And so in particular, this says that S4 is just a quote. So this is a principal bundle. This is a free. So S3 is spin 3. This is a free action. So actually S4 is the quotient, and therefore even the homotopy quotient of S7 by spin 3. It's just saying that it is a principal bundle. And so this derivation, should I jump back one more? Yeah, let me do it. I have maybe 6 minutes left, right? So let's go on. So as we obtained this force sphere here, we actually did get it from a diagram that also had the rational. Well, I didn't explain this. You just have to believe. So here's the rational. It turns out we did find actually the rational version, which is rather trivial, but it's not goes with the rational. It keeps the rational piece of the quaternion configuration, and it was so that certain 2-grain charge seen by the M5 grain is this map to S7, which then goes further down to S4. So actually, there's a sense in which we're really required to globalize this diagram, which captures information both of the S7 and the S4. Okay, it gets a bit esoteric at this point, but no more time to this. But I think maybe you can see it as sort of plausible at least that we say, okay, our S4 is actually S7 mod spin 3, but then it turns out that the spin 5 action that we just mentioned, the spin 5 action that acts here, so there's a canonical spin 5 action on S4, that just rotates it. And it turns out that it lifts to an action of spin 5 on S7, such that the quaternion Hopf vibration is actually equivariant with respect to this action. So spin 5 is SP2, 2 by 2 quaternion matrices that are unitary. We act on the H2, in which this is the unit sphere, from one side, the spin 3 acts diagonally from the other side. So that means we can actually, so that means if we didn't have this flap there, then this coefficient object for a twist, this universal twisting vibration, is actually equivalent, which says that we're doing before Cohomotopy, is actually equivalent to this guy. So due to the equivariance of the quaternion Hopf vibration, it turns out there's a way to do twisted cohomotopy in degree 4 at the same time it being twisted cohomotopy in degree 7, but the twist has to be adjusted in this form. So that's what this top morphism here is showing. A 7 apportioned by these bits. So this allows now a twist by spin 3 by spin 5. So we want our tangent bundle to be twisted this way. So let's see, here's our super space time. So I'm going to the flat piece now, so I'm making it a flat spin bundle. So we're saying, okay, suppose we have this orbifold, which is a flat super spin thing. And so we need, so this sits in spin 8, so we need to be able to split off to make this work, right? To be able to twist, to have cohomotopy here, we need to be able to split off a spin 8 factor by spin 2,1. So we end up with just looking at this rational thing and asking it to globalize.
Is that the flat modality?
Yes,
Okay.
that is the flat modality. Yes. So so this uses some interplay, which I'm just actually observing now in the model. It's just for so this flat G structure. Yeah, I think you asked this before. It just turns out that bundle is not just flat in the standard sense. So this is something that one should check. This follows just from the axioms. This interplay between these two layers of modalities. Right. So you see from the threshold, what I'm trying to motivate is that we're led to considering orbifolds modeled in the space that this frame bundle is equipped with a sequence of lifts, as shown here. But what we said before, you see that these lifts down here, they just reduce the structure group kind of incrementally to spin 2,1 times, and so forth. And then this last lift kind of is the actual co-cycling cohomotopy. So I've given this last lift now a suggestive name here. We want to think of this as being the integral, so the non-infinitesimal version of what used to be this co-cycle in the rational force. So there's a phase space, if you wish, which you can build this way. You quarter everything by diffeomorphism of X, where the field content is this field of gravity here, which we just saw is actually supergravity on this in this flat case. There's one additional guy here, which is something like a degree 4 guy and a degree 7 guy. If you think of it as an irrational cohomology, it's just a degree 4 class and a degree 7. And it turns out that setup, which we kind of discovered here from first principles, we didn't know any string theory, that is precisely the setup that they know that they call M-theorem spin 7 manifolds, space filling in 2 branes. With this 11D manifold decomposed like so, in this part 5D, 3D, 2,1. There's something to be said about branes here, which I'm not going into. And that turns out to be, I'm just saying this, just for entertainment, I'm not explaining it here. But it turns out to be T-dual, what they call F-theorem elliptically 5 and 8 manifolds. And it happens to be actually the phenomenologically interesting sector of type 2 string theory. So I'm saying this kind of it's like my final answer, or it's the last slide. This motivation that I gave at the beginning, that there might be this shortcut that goes all the way down from just modalities to something that actually has some physics in it. So here's our theorem. We just state this, so you can work out what is the data in these lifts here. You can just work this out. These are vibrations. You can pull back Euler classes and see what this data actually is. I'm done in 1 minute. Okay, sorry. So it turns out that data of such a C field is precisely the following. You have a 4 class, 7 class that trivializes the sum of the kappa of the 4 class itself with this P2. That's an anomaly cancellation condition M theory that, well, all these things written in 96, 1 year after his magic year. So there was a claim that this is an M5 brane anomaly that needs to be cancelled. It's just a term that the folklore literature says should be there. It comes out from this lift. It's this lift here. So this lift sort of is a lift going to here. It also gives, that's maybe the most subtle part, it says that the class we're pulling back, this G4, which is really the volume form of that force field, pulled back to space-time now, that isn't an integral class, it turns out. But if you shift it by 1/2 the generator, so 1/4 of P1, then it becomes an integral class. This is a mysterious condition that plays a huge role in string theory that Witten kind of motivated. So he has two sections here. One, in this section he says he believes it's true, and in this section he says he has an argument that it's true. But people, but that means it's true. But there was no way, there was no method. Well, there was an attempt to model. Anyway, here it comes out. And lastly, it says that they call the tadpole cancellation condition. If you regard the lift now actually as a section of this spin bundle here, of this S7 bundle, then it turns out to trivialize the second Euler class, the degree 8 Euler class, which happens to be equal to this under these assumption of structure groups. That's the famous I8 one loop anomaly term. And it gets cancelled. So this is one example of a list of examples we have of stuff that does come out from this kind of reasoning, which seems to be right and promising. Right. And I'll thank you for your attention. Yeah.
Okay. Comments, questions?
Up in the reducing the structure group pictures you were drawing, in general, there'll be obstructions to reducing to some group like SO and there's characteristic classes and all this stuff. Is it clear to you? Have you thought about how that will pop out of this formula?
Well, yeah. So I should say. So there's a constraint here. So these things do not have to exist. These are in this picture. These are the equations of motion. So that's why it's called the covariant phase space. So you might say a priori you're on the space time, and the general field content is just any map to S4. That would be the C field. It would be an off-shell field. And all I want to say, it has to satisfy some conditions. And the conditions, that's the point here. The conditions are meant just all reduced down to just consecutive lifts. So first, the first lift here, this is actually the condition that something satisfies the supergravity equation of motion in the gravitational field. Then the two further lifts, they say, well, the structure group of that bundle needs to be reduced. But if that X happens to be such that this is not possible, then there will not be a solution to these equations of motion. It will just drop out.
And are the obstructions themselves sort of here as well?
I mean, what?
The obstructions themselves, like the need for some class to vanish. Is that class here? You're declaring that these things exist, but is the obstruction also present?
Well, I think that's what if I understand you well, that's what these conditions say. So you ask now, well, it's interesting. It's interesting here, so I did it here. You ask now, what does it actually mean cohomologically to have this lift? And so there's models for this one can work out, and it says that such a lift, so rationally it's actually equivalent to precisely this data. Integrally, this data is implied. So it says you have such a lift. To have such a lift means, for instance, to trivialize this 8 class. Choose a trivialization. That's a choice of lift. And to the further constraint that the cup guy you're using here has to satisfy the shifted individual. So these are. Does that answer the question?
It probably does.
Okay. Yeah.
So does do these two shifts here drop out of considering the ordinary sphere rather than the rationalized sphere? Or
well, yeah. So this condition here, this is a relation that holds in the integral cohomology ring of B spin 4. So what one uses to prove this is the following remarkable fact, which is remarkable in the sense that it's good to know. It's maybe not, you might not think it's super trivial, but this space is actually equivalent to B spin 4. You see this. This is because S4 is itself the quotient of spin 5 by spin 4, and using general concepts of homotopy quotients. So it just so happens that the integral cohomology ring. So you see that means as we're lifting. So as we're forming this section here, this is really B spin 4 topologically. Like if you just consider cohomology classes. So you need to know what is this degree 4 guy that we're pulling back. Turns out the volume form of the force field becomes 1/2 the Euler class. So B spin 4 is the top degree 4 class, which is the Euler class. And there's a theorem which you can find in Felix Harper and Thomas' book on rational motion theory that S4 class is 1/2 the Euler class. But now it's also known in the standard textbooks that integral cohomology, and that's where it's non-rational, where the non-rational information comes in. B B spin 4 ends of our twisting space is generated by two guys over Z by 1/2 P1 and by 1/2 of the Euler class plus 1/4 P1. But this is our, for the previous statement, this is our G4. This becomes the G4. So it says that this is what it says. So if you take G4, 1/4 P1 becomes integral. So that is indeed something that kind of we gain off from going beyond rational.
Okay, let's thank Urs again. So we have time. We begin again at 11:05.
So it's true that whatever implies a big flat in the sense of
Yeah, that's why I called it flat.
yeah. Oh no,
Is that what you mean?
no, I know that, but so yeah, I mean, why not use the at one?
Oh, I see.
Right, because at least naively, it seems like what you're asking for is that, you know, that it's constant on
Yes.
points that it tests for.
Yes. Okay, so that's a very good point. So as I think I amplified this last step, I didn't do synthetically. I just do this.
Yeah.
That's
They
just,
are the same.
and they're it's just flat in the standard single standard sense.
Yeah.
Flat-
Well,